Tonight, we turn our attention to something the mind struggles to hold. A world so vast it bends our understanding of how planets should exist. Its sheer scale defies the rules we once trusted. Imagine a planet so enormous that even the largest world in our solar system could disappear inside it with space still left unclaimed. And yet, in a paradox that feels almost sacred, this colossal body is astonishingly light for its size. In theory, it could drift atop water, if an ocean vast enough to receive it could ever be found. We are familiar with giants. Jupiter has long worn that crown, studied and observed for generations as the ruler of our planetary family. But this distant presence makes Jupiter seem restrained, almost humble. If Jupiter were reduced to the weight of a grapefruit in your hand, this world would loom like a watermelon beside it. Its home lies more than 1,000 light-years away, circling a star unknown to most. Suspended in a stretch of the cosmos, humanity has only begun to awaken to. Before we continue, if journeys like this into the unknown speak to you, a simple like or subscription helps keep this path open. It is small on your end, but its impact reaches far beyond what you see. Now, let us step deeper. To grasp why this discovery carries such weight, we must look backward. For nearly all of human history, our awareness stopped at the borders of our own system. Mercury, Venus, Mars, Jupiter, Saturn, these wandering lights traced patterns across the sky, noticed by ancient eyes, long before science gave them names. Later came Uranus and Neptune, and for a brief time, Pluto stood among them. Yet every one of these worlds was bound to our sun. Beyond that, there was only uncertainty. Other stars filled the heavens, but whether they, too, held planets remained unanswered. Astronomers believed they must. The universe felt far too vast, too crowded with stars, for our system to be the only one chosen to host worlds. Still, belief is not the same as knowing. Assumption carries no proof. The truth is, finding planets beyond our star is a task of staggering difficulty. Picture yourself standing on one coast, asked to notice a firefly drifting beside a lighthouse on the opposite side of a continent. That is the scale of the challenge. Stars blaze with overwhelming brightness. Planets, by contrast, are silent and dim, casting no light of their own. They exist only as faint reflections, ogos of their parent star's glow, a glow that outshines them by billions of times. And yet, against those odds, we found this one, dimmer than the star itself. Then in 1992, everything changed. Astronomers discovered the first confirmed exoplanets, but they were not orbiting a normal star like our own stellar neighbor. They were circling a pulsar, the rapidly spinning remnant of a dead star that had exploded in a supernova. This was exciting, but pulsars are extreme objects. Finding planets around one of them did not tell us much about whether normal stars had planetary systems. The real breakthrough came in 1995 when astronomers Michel Mayor and Dyer Queloz announced they had found a planet orbiting a sun-like star called 51 Pegasi. This planet was nothing like anything in our solar system. It was a gas giant similar in mass to Jupiter, but it orbited incredibly close to its star. So close that it completed an orbit in just over 4 Earth days. So close that its surface temperature was over a This discovery shocked the astronomical community. Nobody expected to find a Jupiter-sized planet so close to its star. In our solar system, gas giants like Jupiter and Saturn orbit, far from our star in the cold outer regions where ice and gas could accumulate during the solar system's formation. Finding one practically hugging its parent star was like finding a polar bear in the Sahara Desert. It should not be there. And yet there it was. This planet, and others like it, discovered soon after, became known as hot Jupiters. They were the first type of exoplanet we found in large numbers, not because they are the most common type of planet in the universe, but because they are the easiest to detect. A massive planet orbiting close to its star creates a bigger wobble. It blocks more light when it passes in front of the star. It leaves bigger fingerprints for our instruments to find. And this brings us to how we found the largest planet ever discovered. The discovery came through a method called the transit technique. This works on a beautifully simple principle. When a planet passes between its star and Earth, it blocks a tiny fraction of the star's light. If you are watching that star carefully, measuring its brightness over time, you will see a small dip as the planet crosses in front. The star dims slightly, then returns to its normal brightness as the planet moves away. The amount of dimming tells you how big the planet is relative to the star. A bigger planet blocks more light, and the timing of these dips tells you how long the planet takes to complete one orbit. This is where the HAT project comes in. HAT stands for Hungarian-made automated telescope, and it is a network of small telescopes designed specifically to search for transiting exoplanets. The project started in 2003 with a single telescope in Arizona. Over the years, it expanded to include telescopes in Hawaii, Arizona, Namibia, Chile, and Australia. This global network allows astronomers to watch stars almost continuously, catching transits that happen at any time of day or night. The telescopes themselves are not particularly large. Each one has a lens about 4 and across, roughly the size of a high-quality amateur telescope. But what they lack in size, they make up for in automation and dedication. These telescopes observe hundreds of thousands of stars every night, measuring their brightness with extreme precision, looking for the telltale dips that indicate a transiting planet between 2005 and 2008. The HAT network collected observations of a star in the constellation Hercules, about 1,044 light-years from Earth. The telescopes noticed that this star was dimming periodically, every 4.81 Earth days. The star's brightness dropped by about 2.5%. That is a large dip. For comparison, when Jupiter transits across the face of our star, as seen from a distant star system, it would block only about 1% of the light. Something was passing in front of this distant star, and whatever it was big. After years of follow-up observations to rule out false positives and confirm the discovery, the planet was announced in 2017, and as astronomers analyzed the data, they realized they had found something extraordinary. Before we step into what this world means, its truths must be laid out with clarity. This planet's sheer scale is undeniable. Its diameter measures about 2.1 times that of Jupiter. Where Jupiter spans roughly 88,000 miles at the equator, this giant stretches close to 185,000 miles from edge to edge. Imagine placing 23 Earths side by side only, then would you match its width? In terms of volume, nearly 12,000 Earths could vanish inside it. By radius, it stands as the largest confirmed exoplanet ever identified, and then the mystery deepens. In defiance of expectation, this immense body carries remarkably little weight. Despite being more than twice Jupiter's size, its mass is only about 45% of Jupiter's. According to the most recent measurements released in 2025, pause on that contradiction. A planet that grows larger, yet becomes lighter. Its density falls to an almost unreal value, about 0.06 grams per cubic centimeter. Water, by comparison, sits at 1 gram per cubic centimeter. In any imaginable ocean, this world would drift effortlessly, buoyant like a beach ball resting on the surface. Its environment is no less extreme. The planet circles an F-type star, hotter and brighter than our Sun. This star holds roughly 1.6 times the Sun's mass and swells to about 1.85 times its diameter. The planet itself clings dangerously closely, around 7 million miles away, completing a full orbit in just 4.81 Earth days. It races around its star with relentless speed. So close, the heat becomes unavoidable. The planet's equilibrium temperature reaches approximately 1,900 Kelvin. On familiar scales, that translates to about 2,960 degrees Fahrenheit, or roughly 1,620 degrees Celsius. Temperatures like this can liquefy most metals. They are intense enough that the planet radiates its own heat, glowing from the punishment of constant stellar fire. Every moment of its existence, this world is being seared, which leads us to the question that lingers beneath it all. How can something so vast be so insubstantial? To understand the puzzle, we look to Jupiter. Our solar system's giant is composed mainly of hydrogen and helium, the lightest elements known. Hydrogen alone accounts for about 90% of Jupiter's mass. Deep within Jupiter, pressure becomes overwhelming. Hydrogen is crushed until it behaves like metal, conducting electricity despite its simple atomic nature. This distant giant shares a similar makeup. Hydrogen and helium dominate its composition. But unlike Jupiter, it has not been squeezed into a compact, heavy core. Instead, it remains swollen, expanded, and loosely bound, a colossal form that resists collapse into density. And in that resistance, the planet reveals its deepest mystery. Rather than collapsing inward, this world has swollen outward like a marshmallow left too long in rising heat. The same material is stretched across an enormous volume, and the result is that ghostly lightness. Its nearby star is the driving force behind this transformation. Heat changes everything. When gas absorbs energy, it spreads. The particles accelerate, pushing farther apart, claiming more space. We see this principle on Earth in simple ways. Warm air lifts hot air balloons skyward because it becomes thinner than the cooler air around it. Now imagine that same process, not in a balloon, but across an entire planet. The upper layers of this world are relentlessly flooded with stellar radiation. That energy excites the gas, forcing it to expand. Over billions of years, this constant heating has slowly inflated the planet into the swollen giant we observe today. And yet, heat alone does not tell the whole story. The degree of inflation is too extreme to be explained so simply. There must be other forces at work. One possibility lies in the planet's path around its star. If that orbit is even slightly stretched instead of perfectly circular, the star's gravity would rhythmically pull and release the planet as it moves closer and farther away. This repeated squeezing and relaxing tidal flexing creates internal friction, much like bending metal back and forth until it warms. This process can generate heat deep inside the planet. Over immense spans of time, that hidden heating could add significant energy to its interior. Another explanation reaches into invisible forces. Gas giants often possess powerful magnetic fields. When these fields collide with the stellar wind, the constant stream of charged particles flowing outward from the star, they may generate electrical currents in the atmosphere. Those currents could carry energy downward, warming the planet from within and helping it remain expanded. A third idea suggests that certain atmospheric layers act like a thermal trap. Heat enters easily but struggles to escape. If energy is held inside longer than expected, the planet stays hotter, lighter, and larger than standard models predict. The truth is simple and unsettling. We do not yet know which of these processes dominates, or whether several act together. This planet remains an open question, a living puzzle at the edge of our understanding, because it represents one of the most extreme inflated worlds ever found. It serves as a rare testing ground and, offering to those trying to decipher how such planets endure. So close to its star, the planet is almost certainly tidally locked. One hemisphere is eternally exposed to light, the other is forever turned away into cosmic night. Our moon behaves this way with Earth, always presenting the same face. But here, the consequences are far more severe. The day side is under constant assault. Radiation pours down without pause, driving temperatures into the thousands of degrees. The night side never sees direct starlight. It should be far colder though. Powerful winds carry heat from the blazing hemisphere, preventing it from freezing entirely. Between these two extremes lies the terminator, a narrow band of endless twilight. Across this boundary, atmospheric currents roar from hot to cool, likely reaching speeds of thousands of miles per hour. The planet's atmosphere is not calm or layered, it is a raging, churning storm shaped by eternal day and endless night. And when we speak of this atmosphere, it must not be confused with anything familiar. There is no breathable air. Oxygen is virtually absent. Hydrogen and helium dominate, mirroring the planet's internal composition, but under temperatures nearing 3,000 degrees Fahrenheit, chemistry behaves in unfamiliar ways. Substances we know as solids or liquids are stripped into gas. Compounds like titanium oxide and vanadium oxide used on Earth in paints and industry may drift freely through the atmosphere, absorbing starlight and intensifying the heat even further. Some researchers believe the hottest gas giants host skies where iron and magnesium exist as vapor. Iron strong, rigid, unyielding, reduced to an invisible gas. On the scorching day side, this vaporized metal could cool just enough to condense, falling as molten droplets through the atmosphere. Iron rain. There may also be clouds, unlike anything we know formed from vaporized silicates on Earth. Silicates are stone, sand, glass. Here, they may rise as mist and gather as clouds, sculpted not from water, but from rock itself. This is not merely a planet. It is a reminder that the universe reshapes even the most familiar elements into forms we are only beginning to comprehend. They would not be clouds as we know them, but veils of pulverized stone suspended in a hydrogen-rich sky, carried by winds screaming faster than sound itself. The appearance of this world is likely alien beyond imagination. Its colors may bear no resemblance to anything familiar, depending on which elements dominate its atmosphere and how they interact with light. The planet could appear almost void dark, swallowing most of the starlight that reaches it. Or it might shine with unnatural hues, glowing faintly as superheated gases radiate their own energy back into space. For now, these visions remain conjecture. We cannot yet capture a direct image of the planet. What we know comes from models, mathematics, and comparisons to similar worlds already studied. Discovering this planet and measuring its basic traits was only the opening chapter. To truly understand it, astronomers must listen to its atmosphere itself. And astonishingly, we have learned how to do exactly that. Each time the planet crosses in front of its star, a small fraction of starlight passes through its swollen atmosphere before reaching us. Different gases leave distinct fingerprints, absorbing specific wavelengths of light. By dissecting this altered starlight, scientists can determine which elements are present. This method, known as transmission spectroscopy, has already revealed water vapor, sodium, potassium, and other substances in distant planetary skies. A planet of this size, with such an expanded atmosphere, is a near-perfect subject for this technique. The more atmosphere light must pass through, the clearer the signals become. The James Webb Space Telescope, launched in 2021, is uniquely suited to probe this world with unprecedented sensitivity. What it reveals will echo far beyond a single planet. These findings will help illuminate an entire class of worlds known as inflated hot Jupiter's planets, pushed to the very edge of what physics allows. By studying such extremes, we learn not only about them, but about the forces that shape every planet, everywhere. To grasp why this discovery stands apart, it helps to return home for comparison. Jupiter reigns as the giant of our solar system. It contains more mass than all the other planets combined. Hollow it out, and roughly 1,300 Earths could fit inside. It commands a vast family of at least 95 moons, and hosts the Great Red Spot, a storm larger than Earth that has endured for centuries. Jupiter is extraordinary, and yet, this distant world dwarfs it. Its diameter exceeds Jupiter's by more than double. By volume, you could fit around 9 Jupiters inside it. The difference in scale is staggering. Other giants exist beyond our system. WASP-79b, an inflated hot Jupiter roughly 790 light-years away, reaches about twice Jupiter's radius but still falls short. WASP-17b, discovered in 2009, once held the title of largest known exoplanet at about 1.89 times Jupiter's diameter. Then there is KELT-9b, one of the hottest planets ever found, with dayside temperatures exceeding 7,800 degrees Fahrenheit, hotter than some stars. Its diameter reaches roughly 1.89 times Jupiter's as well. Extreme, violent, luminous yet still smaller than the world we are considering. There have been objects that appeared larger, but closer examination revealed them to be brown dwarfs. These are not planets, but something in between, too massive to be planetary, yet too small to ignite like stars. Brown dwarfs typically carry at least 13 times Jupiter's mass. Some are bloated, some are luminous, but they are not worlds in the planetary sense. This record-breaking giant, at only about 0.45 times Jupiter's mass, according to the latest measurements, does not cross that boundary. It lacks the mass required to be anything other than a planet expanded to a near-mythic degree by the relentless light of its star. This raises a deeper question. How large can a planet truly become? Physics sets the boundary. As a gas giant gains mass, gravity tightens its grip. Rather than expanding, the added weight compresses the interior, increasing density instead of size. Jupiter itself sits near the upper limit of what simple mass accumulation can achieve. Add more hydrogen and helium, and Jupiter would barely grow, it would simply become heavier and denser. Planets that surpass Jupiter's size do so not by mass alone, but by external influence. Remove the intense radiation bathing this distant giant, allow it to cool over billions of years. It would shrink, settling into a form similar to or even smaller than Jupiter. Inflated hot Jupiters reveal just how dramatically environment can reshape a world. The same matter, under different conditions, becomes something entirely new. This planet likely did not begin where it now burns. At a distance of only 7 million miles from its star, the early disk of gas and dust would have been too hot for ESOs to form, too sparse in solids, to quickly build a massive core, and yet the planet exists there now. The prevailing explanation is migration. Long ago, the planet likely formed far from its star, in colder regions where gas giants are born. Over time, interactions with the surrounding protoplanetary disk altered its path. As it moved through the disk, gravitational forces created spiral density waves, regions of slightly enhanced or reduced gas density. These waves tugged at the planet, draining angular momentum from its orbit. Losing angular momentum meant drifting inward, slowly, relentlessly, over millions of years. This inward spiral, known as Type II migration, is believed to be common in young planetary systems. Many hot Jupiters may have followed similar journeys, though each path carries its own subtleties. This world's story is not just one of size or heat. It is a testament to motion, transformation, and the unseen forces that shape destinies on a cosmic scale. The timing of this planet's passage across its star aligns perfectly with the rhythm revealed by the star's subtle wobble. Two independent methods, telling the same story. The orbital period measured through transits matches the period derived from radial velocity curves. Its size and mass agree with what we would expect from a gas giant of astonishingly low density. Nothing contradicts itself. Every piece locks into place. These techniques are not new guesses. They have been tested repeatedly across countless systems. Transit measurements have been checked against direct images where possible. Stellar sizes have been confirmed through asteroseismology, a study of tiny vibrations rippling through stars. Mass calculations have been validated using binary stars, where gravity allows direct measurement through orbital motion. This foundation is solid. The science is mature. We can say with confidence that this planet truly is as immense and as insubstantial as it appears. And this is only the beginning. With the James Webb Space Telescope, astronomers can move beyond basic measurements and begin reading the planet's atmosphere in detail. During each transit, starlight slipping through the planet's gaseous envelope carries the signatures of the molecules within it: water vapor, carbon dioxide, methane, sodium, potassium, titanium oxide, vanadium oxide. Each leaves a distinct imprint in the spectrum, like sacred markings etched into light itself. By decoding these patterns, scientists can assemble a detailed inventory of the atmosphere. Even more may be revealed. Different wavelengths, probe different altitudes, allowing researchers to reconstruct how temperature changes with height. Layer by layer, a thermal map emerges, showing how energy moves through the planet's atmosphere. This deepens our understanding of the forces keeping the planet swollen and luminous. There is also the possibility of weather. If this world hosts massive atmospheric structures, bands, storms, or long-lived features akin to Jupiter's Great Red Spot, they could subtly alter the shape of each transit. One passage might not look exactly like the next. Detecting such variations would offer a rare glimpse into the planet's dynamic skies. Observations from the ground add another dimension. High-resolution spectroscopy can measure tiny Doppler shifts in atmospheric gases as the planet moves along its orbit. This technique can detect molecules that leave only faint spectral traces and can even reveal wind speeds by tracking how gases move toward or away from us. In this way, astronomers can sense motion on a world more than 1,000 light-years away. Continued monitoring may also uncover companions. Most planetary systems are not solitary. Ours has 8 planets. Others host 5, 6, or more. If additional planets circle this star, they may betray themselves through extra transit signals or through small rhythmic changes in the giant's orbit as gravity tugs back and forth. There is even the faint possibility of moons. A large moon could leave its own signature in the starlight. The confirmed detection of an exomoon would mark a historic moment, a new class of world revealed. Though none have yet been verified, planets like this one, with deep transits and long observation histories, are among the best places to search. The investigation is far from complete. Each observation refines the picture. Each measurement tightens the constraints. This planet has already been studied for nearly a decade since its announcement, and it will remain a focus for decades to come. Even more powerful tools are on the horizon. The European Extremely Large Telescope, now rising in Chile, will wield a mirror nearly 130 feet across, capable of directly imaging some exoplanets and probing their atmospheres with unprecedented clarity. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will hunt for planets using gravitational microlensing, uncovering worlds far from their stars that other methods cannot detect. This planet, first revealed with relatively modest ground-based instruments, will be examined by the most advanced observatories humanity has ever built. This is how science unfolds. Each discovery becomes a foundation. Every answer opens new questions, and mystery deepens, even as understanding grows. Step back now, and consider the larger awakening this represents. Before 1995, we knew of exactly 0 planets beyond our solar system. We had theories, we had intuition, but we had no proof. Today, only a few decades later, more than 5,700 exoplanets have been confirmed, with thousands more awaiting verification. We have found worlds of every imaginable kind. Rocky planets smaller than Earth, gas giants larger than Jupiter, planets that race around their stars in hours, and others that take centuries to complete a single orbit. Worlds in habitable zones where liquid water might persist. Planets circling binary stars beneath twin suns. Planets so close to their stars that their surfaces are molten. Even rogue planets, drifting alone through the darkness without any star at all. The message is unmistakable. Planetary systems are common. Nearly every star you see in the night sky likely hosts at least one planet. Our galaxy alone contains between 100 and 400 billion stars. If most have planets, then hundreds of billions of worlds exist in the Milky Way, and beyond it lie at least 2 trillion galaxies. The number of planets stretches beyond comprehension. Somewhere among them, life may exist. That possibility is one of the great motivations driving this search. We seek Earth-like worlds, places where conditions might allow life as we understand it. This planet is not one of them. It has no solid surface. Its temperatures are lethal. Its atmosphere is dominated by hydrogen and exotic vapors. Life as we know it could not survive there, yet it still matters. By studying extreme worlds like this, we learn how planetary systems form and evolve. Hot Jupiters likely did not originate where we find them today. They formed far out, then migrated inward over millions of years. That migration can profoundly reshape a system, scattering smaller planets, altering orbits, or erasing worlds that once existed. Understanding how often this happens and how violent the process is, helps us judge how many systems might preserve calm inner regions where Earth-like planets could survive. This discovery is not an isolated wonder. It is a single piece in a vast cosmic mosaic, helping us map the extraordinary diversity of worlds that exist. And it invites one final question. What would it truly be like to stand beneath the skies of such a planet? Even imagining the journey pushes beyond the limits of what humanity has ever attempted. And yet, through light alone, across 1,000 years of darkness, we have already begun to know it. Some worlds rush inward, pulled tight against their stars in cosmic haste. Others drift more slowly, halting partway through their journey. A few may even move outward, guided by subtleties in the surrounding disk. Migration is not a single path, but a spectrum of outcomes shaped by delicate conditions. There is also another unseen hand to consider. Additional planets still hidden from our instruments may exist within this system. Their gravitational influence could have reshaped this giant's orbit over time, stretching it, stirring tidal heating, or nudging it closer to its star. The system remains under careful observation. Future data may reveal faint irregularities in the planet's motion, whispers of companions we have not yet seen. What now appears simple may, in time, reveal deeper complexity. One of the enduring questions surrounding hot Jupiters like this one is whether they can last. Their existence is precarious. Orbiting so close to their stars, they endure relentless extremes. In some cases, stellar radiation peels away their atmospheres, sending vast streams of gas into space. Over billions of years, this erosion can dramatically reduce a planet's mass, sometimes leaving behind only a stripped core, or erasing the planet altogether. This world's extraordinarily low density may make it especially exposed. Its gravity, spread thin across an immense volume, is weaker than that of denser giants. The escape velocity, the speed particles must reach to break free, is lower. Gas does not need to fight as hard to leave. Yet, there is a balance. Compared to the most extreme ultra-hot Jupiters, this planet orbits at a slightly safer distance. Some planets complete an orbit in less than a single day, enduring radiation so intense that telescopes have captured tails of gas streaming behind them. Against those extremes, a nearly 5-day orbit offers relative stability. For now, this planet is not on the brink of dissolution. The nature of the star itself also matters. F-type stars shine brighter than our sun, but burn faster. Their lifespans are shorter, their fuel consumed at a quicker pace. This star is estimated to be around 3 billion years old, with several billion more years of stability remaining, but that time is finite. When the hydrogen in its core is exhausted, the star will swell into a red giant. As it expands, it will consume nearby planets. No matter how immense this world appears, it will eventually be claimed by its star. This fate is not unusual. Our own solar system carries the same sentence. In roughly 5 billion years, our sun will expand, likely engulfing Mercury and Venus and, perhaps Earth. Every planetary system lives on borrowed time, its ending written into the lifespan of its star. This giant exists now. In this narrow chapter of cosmic history, a billion years from today, it may look unrecognizable. 2 billion years from now, it may be gone entirely. We are witnessing it during a fleeting window, and that alone makes it precious to study. The distance to this world defies intuition. It lies about 1,044 light-years away. A light-year is the distance light travels in a single year, moving at roughly 186,000 miles per second. At that speed, light circles Earth more than 7 times every second. It crosses the gap to the moon in just over a second. Yet even with such velocity, interstellar space demands patience. Sunlight reaches Earth in a little over 8 minutes. Light from Proxima Centauri, our nearest stellar neighbor, takes more than 4 years. Light from this distant system has been traveling for over 1,000 years. When we observe it tonight, we see it as it was around the year 1000. Before the Norman Conquest, before Europe's first universities, before the Crusades. That is how deep into the past our gaze extends. Astronomy is always an act of looking backward. For this planet, every measurement reflects a version of it that existed a millennium ago. If a dramatic event occurred there yesterday, its signal will not arrive for another 1,000 years. These distances also enforce isolation. Even if travel at light speed were possible, which physics forbids for anything with mass, the journey would take over 1,000 years. With any technology we can realistically imagine, it would take far longer. Voyager 1, the fastest spacecraft humanity has launched, travels at about 17 miles per second. At that pace, reaching this star would require more than 11 million years. This makes direct exploration impossible. No probes, no samples, no close-up images. Everything we know comes from interpreting a faint stream of light that has crossed 1,000 light-years of emptiness. And yet, that light has told us much. We know the planet's size, its mass, the length of its year, the temperature of its atmosphere. We are beginning to uncover its chemical makeup. This is a testament to human ingenuity. From whispers of starlight, we can reconstruct a world no human will ever touch. You might wonder how such confidence is possible. How can we be sure about a planet so distant? The answer lies in rigor and repetition. Modern astronomy relies on multiple, independent techniques that converge on the same truth. The planet's size comes from the transit method. When the planet crosses its star, it blocks a fraction of the starlight. That fraction depends on simple geometry, the ratio of the planet's disk to the star S. It is no more mysterious than holding a ball in front of a lamp and measuring the shadow. We know the star's size from well-tested stellar models, refined over more than a century. Spectroscopy reveals its temperature and composition. Distance measurements allow astronomers to calculate its true brightness. Together, these methods consistently point to a star about 1.85 times the sun's diameter. Given that size, the depth of the transit yields the planet's diameter about 2.1 times that of Jupiter. This result is robust. The planet's mass is measured differently. Using the radial velocity method, astronomers observe the star's subtle wobble caused by the planet's gravity. As the star moves toward and away from us, its light shifts slightly due to the Doppler effect. The strength of that wobble reveals the planet's mass. Once the orbit is known from transit timing, these two techniques, transits and radial velocities, and when independent methods tell the same story across unimaginable distances, we listen. At a distance exceeding 1,000 light-years, even the fastest craft humanity has ever launched would be hopelessly slow. Moving at Voyager 1's speed about 17 miles per second, the journey would last more than 11 million years. Longer than our species has existed. The gulf is absolute. And yet, for a moment, imagine the impossible, that you could arrive instantly, as stories of science fiction allow. The first presence to announce itself would be the star. It would blaze hotter and brighter than our sun, shining an intense white light with a faint blue edge. Its energy would dominate the system, saturating space with radiation. Drawing closer to the planet, scale would begin to reveal itself. From a million miles away, it would no longer look like a point of light, but a true world, rounded and immense. From 100,000 miles out, its curved horizon would swell across your vision, overwhelming your sense of proportion. Its appearance would defy familiarity. Jupiter wears belts of brown, cream, and rust red, stretched into bands by rapid rotation and layered chemistry. This planet might share faint echoes of that pattern, or it might look smooth, chaotic, or entirely foreign. The colors could be dark and absorbing, or luminous and strange, shaped by gases and temperatures unseen in our solar system. If you could descend into the atmosphere, the environment would turn hostile almost immediately. Even near the upper layers, heat would be intense. With depth, pressure would climb relentlessly, the gas would thicken. Light from the star would dim into a permanent dusk, then vanish altogether. There would be no surface awaiting you. Gas giants offer no solid ground. Instead, the atmosphere grows denser, hotter, heavier, without boundary. Eventually, the distinction between gas and liquid would dissolve, replaced by a supercritical fluid matter behaving as both at once. Deeper still, the unknown begins. In some gas giants, hydrogen is crushed so tightly that it becomes metallic, conducting electricity like a solid despite being made of the lightest element. Whether such a layer exists here remains uncertain. Its remarkably low density suggests a small or diffuse core, if one exists at all. The planet's interior is hidden from direct view. We infer its nature only through mass, radius, and behavior. Different models offer different answers. Future observations may favor one over another, but for now, the interior remains sealed in mystery. This world teaches a broader truth. Modern astronomy has revealed again and again, the universe is far more diverse than we once believed. When our knowledge was limited to the solar system, planets seemed orderly and predictable. Now, every category has fractured into countless variations. Gas giants can be cold and distant like Jupiter, or blisteringly hot and pressed close to their stars. They can be dense and compact, or swollen and fragile. They can migrate, collide, or be cast adrift into interstellar darkness. Rocky planets show the same diversity. Some are smaller than Earth, others far larger. Some are dry and airless, others drowned beneath deep oceans or wrapped in suffocating atmospheres of carbon dioxide, nitrogen, or stranger gases still. Ice giants, water worlds, carbon-rich planets with diamond-like interiors. This discovery stretches our expectations further. With every new instrument, the universe offers something unexpected. This planet stands as one such revelation. The largest confirmed planet by radius, a world so inflated that, in theory, it could float on water despite surpassing every other known planet in size. A reminder that when physics is pushed to extremes, it produces forms that feel almost impossible. The search for exoplanets is one of humanity's great awakenings. In just a few decades, we have moved from knowing only our own planetary family to cataloging thousands of worlds around distant stars. We have learned to read atmospheres across light years. We have found planets and regions where liquid water could exist. We have expanded the very definition of what a planet can be. This discovery is one marker along that path. It may hold a record today, but its true value lies deeper. It reveals how gas giants evolve, how planetary systems are shaped, and how extreme the universe can become. When discoveries like this are announced, a familiar question often follows. Why does it matter? Why devote time and effort to worlds we will never reach? The answers are layered. First, there is curiosity itself. The desire to understand is woven into our nature. It is the same impulse that fueled every scientific advance humanity has ever made. Knowledge has value simply because it expands our awareness. Each distant planet adds to the shared understanding of our species. Second, exoplanets give us perspective. With only one solar system, we cannot know which features are universal and which are unique accidents of history. Studying many planetary systems allows us to test ideas, refine theories, and discover phenomena like extreme planetary inflation that our own system never revealed. Third, the tools developed for this research often reach far beyond astronomy. Precision measurement techniques find uses in medicine, engineering, and technology in ways no one could predict in advance. This has always been the hidden power of basic science. And finally, there is the deepest reason of all. Exoplanet research is part of the larger human question: what is our place in the universe? Are worlds like Earth rare or common? Is life unique to us, or scattered across the stars? This giant planet cannot host life as we know it, but understanding worlds like it helps us identify which systems might. Every planet studied is a piece of the greater puzzle, and even worlds we will never touch can still illuminate who we are and where we belong. There is another reason discoveries like this matter, one that reaches beyond data and theory. They inspire. The children growing up today are entering a world where thousands of exoplanets are already known. A world where astronomers routinely analyze the atmospheres of planets orbiting distant stars. Where the search for life beyond Earth is no longer a philosophical question, but an active scientific effort. Some of those young people will become the scientists who push this frontier forward. They will design new telescopes, invent sharper techniques, and ask questions we have not yet imagined. Showing them that the universe is rich with mysteries waiting to be understood is itself a powerful outcome of research like this. This planet is one of those mysteries, a world that resists easy explanation and stretches our understanding of what planets can be. Every child who learns about it learns something profound. The universe is larger and stranger than they once believed, and that realization opens a door. There is also a deeper connection at work, one that modern astronomy has revealed with unmistakable clarity. Every atom in your body was forged in a star. The carbon in your cells, the oxygen in your lungs, The iron in your blood, none of it was created on Earth. These elements were born in stellar cores or in the explosions of dying stars billions of years ago. Those stars scattered their material across space. Over unimaginable spans of time, that matter drifted, condensed, and eventually became our solar system, our planet, and finally us. You are made of star stuff. This is not metaphor or poetry. It is literal fact. The giant planet we have been discussing is made of the same material. Its hydrogen is the same hydrogen found in water. Its helium is identical to the helium that fills party balloons. At the most fundamental level, there is no difference between the matter composing that distant world and the matter composing you. We are connected to the cosmos not only through observation, but through substance. We are not separate from the universe, we are part of it. When we study distant planets, we are studying the same physical processes that ultimately gave rise to us. This may be the deepest lesson astronomy has to offer. We are not passive observers watching a distant spectacle. We are participants in a story that began with the Big Bang and continues to unfold. The same laws of physics that shape gas giants govern the behavior of atoms in your body. The same gravity that binds planets to their stars holds you to the earth beneath your feet. Understanding this changes perspective. The universe feels less distant, less alien. It becomes a single, interconnected whole. So when you return to daily life, carry this awareness with you. Somewhere far beyond our reach, more than 1,000 light years away, a planet larger than Jupiter circles its star. It existed long before humans walked the earth and will endure long after we are gone. It does not know we exist, but we know about it. And in that act of knowing, of caring, we briefly rise above our small place in the vastness. We live at a unique moment in history. We are the first generation to know with certainty that planets orbit other stars, the first to catalog entire planetary systems beyond our own, the first to study the atmospheres of worlds we will never visit. This knowledge reshapes how we see ourselves. We are not alone in a universe of empty suns. We inhabit a cosmos filled with worlds, many utterly alien, some perhaps familiar enough to host life. The universe has always been there, waiting. Only now are we beginning to explore it. Thank you for taking this journey. If you found it meaningful, your support helps make more explorations like this possible. And when you have the chance, look up at the night sky. Think about the planets that may orbit those distant points of light. Wonder about what exists beyond our world. That sense of wonder, that curiosity, and openness to the unknowns among the finest qualities we possess. Good night, and may you never look at the stars quite the same way again. But before we truly close, there is more context that makes this discovery even richer. The story of how humanity learned to find planets around other stars is a story of patience, ingenuity, and repeated failure before success. For much of the 20th century, astronomers searched diligently and found nothing. Again and again, proposed detections collapsed under scrutiny. In the 1940s and 1950s, several astronomers claimed to have detected planets using astrometry, a method that looks for tiny shifts in a star's position caused by an orbiting companion. The most famous case involves Barnard's star, one of our nearest neighbors. Peter van de Kamp spent decades measuring its motion and eventually announced the presence of 2 Jupiter-sized planets. The claim electrified the scientific community. If planets orbited nearby stars, they might be everywhere. But the excitement faded. Other astronomers could not reproduce his results. Over time, it became clear that the apparent stellar wobble was caused not by planets, but by subtle changes to the telescope itself. Adjustments and repairs had introduced systematic errors that mimicked planetary signals. Van de Kamp never accepted this conclusion and defended his findings until his death in 1995, just months before the first confirmed exoplanet around a sun-like star was announced. Planets were real after all, just not the ones he had claimed. That episode left a lasting mark on the field. Astronomers became cautious. Claims required multiple independent confirmations. Every possible source of error was scrutinized. This culture of skepticism shaped the landmark discovery of 51 Pegasi b in 1995. Michel Mayer and Didier Queloz detected it using the radial velocity method, measuring tiny Doppler shifts in the star's light. They knew the signal could be deceptive. Stellar activity, pulsations, or unseen companions might mimic a planet. So they checked everything again and again before announcing their result. Even then, skepticism remained. But when other teams turned their instruments toward the star, the signal was confirmed. The impossible-seeming planet was real. That same rigor defines exoplanet science today. When surveys first detected the transit of the giant planet discussed here, no immediate announcement followed. Years of follow-up observations came next. Radial velocity measurements confirmed its mass. Alternative explanations were ruled out. Only when multiple techniques all pointed to the same conclusion was the discovery made public. That is why we can trust it. This planet joins a growing family of record holders that help place it in context. The hottest known exoplanet, KELT 9b, has a dayside hotter than many stars, so hot that molecules tear apart into individual atoms, and the planet slowly evaporates into space. At the opposite extreme, lie frigid worlds barely detectable at all. Together, these extremes remind us how vast the range of planetary conditions truly is. And this is why discoveries like this matter. Not because we will ever go there, but because they expand the boundaries of what we know, what we imagine, and what we understand about our place in the universe. Yet this giant is not alone among planetary extremes. At the opposite end of the temperature scale lies OGLE 2005 BLG 390LB, discovered through gravitational microlensing in 2005. Its estimated surface temperature is about 364 degrees Fahrenheit, or roughly 50 Kelvin colder than Pluto. It orbits far from a faint red dwarf star, receiving almost no warmth. It is almost certainly a frozen, lifeless world, locked in permanent cold. Worlds like this remind us that planets do not require heat or proximity to a star to exist. They persist even in deep cosmic cold. Density provides another extreme. The densest known exoplanet remains a subject of debate, but one leading candidate is Kepler 131c, which may have a density exceeding 30 grams per cubic centimeter. For perspective, iron has a density of about 7.9, and lead about 11.3. A planet this dense would need to be composed of extraordinarily compressed material, perhaps heavy elements crushed under immense pressure into exotic states of matter. How such planets form remains an open question. They challenge our understanding of planetary interiors and push the limits of known physics. At the other extreme are the least dense worlds. Aside from the giant we have focused on tonight, WASP-193b stands out with a density of roughly 0.059 grams per cubic centimeter, nearly identical to our record holder. These planets are astonishingly inflated, more like cosmic balloons than conventional gas giants. Why some hot Jupiters swell to such extremes while others remain compact is one of the most active areas of research in exoplanet science. Orbital extremes are just as dramatic. K22137b currently holds the record for the shortest confirmed orbital period around a main sequence star. It circles its star once every 4.3 hours, completing more than 5 orbits per Earth day. At such close range, it is almost certainly tidally locked, with one side perpetually scorched and the other locked in eternal night. At the opposite end of the spectrum are planets in extremely wide orbits, detected through direct imaging. Some take thousands of years to complete a single orbit, circling their stars at distances of hundreds or even thousands of astronomical units. These distant giants may form through entirely different mechanisms, possibly by direct gravitational collapse rather than the slower process of core accretion. Each of these extreme planets teaches us something fundamental. The hottest planets show us how atmospheres behave when molecules are torn apart. The coldest planets reveal what happens when a world receives almost no stellar energy. The densest planets probe the limits of matter under pressure, and the least dense planets, like the one at the heart of this story, force us to rethink how atmospheres store and transport energy. Together, these outliers define the boundaries of what planets can be. Any successful theory of planet formation must explain not just the average case, but these extremes. The host star itself is a crucial part of the story. This planet orbits an F-type star, a class that sits between Sun-like G-type stars and hotter E-type stars. F-type stars are more massive than our Sun, hotter, and more luminous. With surface temperatures between about 6,000 and 7,500 Kelvin, they shine more intensely, flooding nearby planets with energy, but they also live shorter lives. While our Sun will remain stable for roughly 10 billion years, an F-type star typically lasts only 5 to 7 billion years before evolving into a red giant, potentially engulfing any close-in planets. These stars occupy an important niche. They are bright enough to study in detail, but not so hot that their radiation overwhelms planetary signals. Although they make up only about 3% of the stars in the Milky Way, that still amounts to billions of F-type stars across our galaxy. This particular star rotates relatively slowly, an important advantage. Rapid stellar rotation smears spectral lines, making precise radial velocity measurements difficult. Slower rotation allowed astronomers to detect the subtle Doppler shifts caused by the planet's orbit. The star's metallicity, the abundance of elements heavier than helium is, also near solar. Stars with higher metallicity are more likely to host giant planets, likely because their protoplanetary disks contained more solid material to build planetary cores. Star and planet are inseparable. The star's luminosity controls how much energy the planet receives. Its age tells us how long the planet has had to evolve. Its rotation and activity affect how easily we can measure the planet's properties. To understand the planet, we must understand the star. Over the past decade, theorists have worked intensively to explain inflated hot Jupiters like this one. When the first examples were discovered, they immediately broke existing models. Gas giants were supposed to have predictable sizes for a given mass and age. Jupiter fits those predictions remarkably well, but these hot Jupiters were too large. Stellar heating alone could explain some inflation, but not the most extreme cases. Even sophisticated models fall short. Something else must be happening. One leading idea is that energy absorbed in the upper atmosphere is somehow transported deep into the planet's interior, preventing it from cooling and contracting. How this energy moves through winds, waves, magnetic effects, or other processes is still not fully understood. And that uncertainty is precisely what makes this planet so valuable. It is not just a record holder. It is a challenge. a reminder that nature is under no obligation to conform to our expectations and that the universe still has much to teach us. In the simplest planetary models, most of the energy dumped into a hot Jupiter's upper atmosphere is expected to escape almost immediately, radiating back into space before it can affect the deeper layers. The interior, in those models, cools and contracts over time. But if even a portion of that stellar energy is somehow carried downward, the planet would swell from the inside, held open by hidden heat. The question becomes almost prophetic in nature. What unseen process keeps the fire burning below the clouds? One proposed answer is ohmic dissipation. Under relentless stellar radiation, the planet's upper atmosphere becomes partially ionized, turning it into a vast, electrically conducting shell. As fierce winds drive this charged gas across the planet's magnetic field, electric currents are generated. Those currents do not flow freely forever, they lose energy as heat. That heat seeps inward, warming the planet's interior and slowing its contraction, like an unseen furnace buried beneath the atmosphere. Another possibility lies in the deep coupling between sky and core. The brutal contrast between permanent day and endless night drives global winds of staggering power. These atmospheric rivers may not stop at the clouds. Instead, they could interact with deeper layers, exchanging momentum and energy in complex ways that prevent the interior from shedding its heat. The planet, in this view, is not layered and isolated, but dynamically connected from its glowing skies down to its hidden depths. A third explanation looks not to motion, but to composition. Certain atmospheric molecules, if present at just the right altitudes, could trap heat efficiently by absorbing radiation and re-emitting it in ways that slow energy loss. The atmosphere itself would then act as a thermal veil, allowing the planet to retain warmth far longer than expected. Increasingly, researchers suspect no single explanation reigns alone. Instead, different planets may be shaped by different combinations of these processes, woven together according to their individual conditions. A unified theory remains elusive, and the work is ongoing. This is where simulations become acts of modern divination. Astronomers construct intricate three-dimensional models of alien atmospheres, following the flow of energy, the birth of winds, and the evolution of chemistry. Across the globe, they model interiors as well, tracing how heat rises, spreads, and reshapes the planet over time. These virtual worlds are then tested against reality. When a model fails to reproduce what telescopes observe, it is a sign that some hidden truth is still missing. Our record-holding giant is therefore not just a curiosity, it is a trial by fire for theory itself. Any explanation that works for ordinary hot Jupiters must also account for this extreme case. If it cannot, it is incomplete. At first glance, this planet seems utterly irrelevant to the search for life. It has no solid ground. Its temperatures would shred complex molecules. Its atmosphere is dominated by hydrogen and unfamiliar vapors, hostile to biology as we understand it. Nothing living could endure there. And yet, its existence quietly informs one of our most sacred questions. To understand where life can arise, we must also understand where it cannot. Hot Jupiters like this one almost certainly did not form where we see them today. They were born far from their stars and later spiraled inward. That journey would have been destructive. Any small, rocky worlds in their path, especially those in the habitable zone, would have been scattered, consumed, or flung into darkness. If such migrations are common, many planetary systems may have lost their chance at life before it ever began. Our own solar system tells a different story. Jupiter formed far out and stayed there. That stability may not be an accident. Had Jupiter migrated inward early on, the material that became Earth might never have assembled. Understanding why some giants move while others remain anchored helps us identify which systems are most likely to host living worlds. Stellar mass, chemical richness, and even galactic environment may all play a role. These patterns guide where we look next. There is also a deeper revelation here. For a long time, astronomers assumed other planetary systems would resemble our own small rocky worlds near the star, gas giants farther out. Hot Jupiters shattered that quiet assumption. They revealed architectures we never imagined, arrangements that once seemed impossible. In doing so, they expanded our sense of what the universe allows. If planets can exist in forms this strange, then perhaps life, too, may find footholds in places we have not yet dared to imagine. By cataloging the full range of planetary diversity, including worlds that are hostile and extreme, we refine our vision of what is possible. Even inhospitable planets serve the greater awakening. They teach us the boundaries, and in doing so, illuminate the paths within them. Since its announcement in 2017, this star and its swollen companion have been watched with growing intensity. Ground-based telescopes have sharpened transit measurements. Space observatories have searched for subtle variations that might betray unseen planets or moons. Spectrographs have sifted starlight for chemical signatures. The Hubble Space Telescope has scanned its atmosphere during transits, hunting for water vapor and other molecules and signals barely above the noise. Before its retirement, the Spitzer Space Telescope observed the planet in infrared light, revealing how heat is redistributed between its eternal day and endless night. Now, the James Webb Space Telescope stands ready to deepen the revelation. Its instruments can dissect exoplanet atmospheres with extraordinary precision, exposing their chemistry, thermal structure, and perhaps even signs of dynamic weather. From the ground, ultra-high-resolution spectrographs continue their vigil, tracking atmospheric winds through minute Doppler shifts. Photometric monitoring searches patiently for timing anomalies, whispers of additional planets or moons tugging at the giant's path. So far, nothing else has revealed itself. But the silence is not an ending, it is an invitation. This system is still unfolding its truth, and we are still learning how to listen. Over time, the weight of evidence has sharpened our view of this extraordinary world. What began as a rough estimate has steadily evolved into a precise portrait. Early measurements suggested a planet with about one-third the mass of Jupiter. Today, after years of careful observation, astronomers have refined that value to roughly 0.45 times Jupiter's mass. Its radius is now measured with far greater accuracy. Its orbit is tightly constrained. Each uncertainty has narrowed. Each parameter has settled into place. This is how science moves forward, not through sudden leaps, but through patient refinement. One observation at a time, one uncertainty reduced, one blurred outline brought into focus. A distant point of light becomes, gradually, a well-characterized world, and this process is far from finished. Future telescopes will sharpen the picture even further. New analytical techniques will extract more meaning from data we already possess. What we learn from this extreme planet will not remain isolated. The insights gained here will be carried forward and applied to countless other worlds. The tools refined on the swollen giant will one day be used to probe smaller, cooler planets, perhaps, even Earth-like worlds, orbiting quietly within habitable zones. In science, no discovery is an endpoint. Every answer is a threshold. The transit method itself is a powerful illustration of this. When a planet crosses in front of its star, the event is far more than a simple dimming of light. Hidden within that tiny dip is a wealth of information. The depth of the transit reveals the planet's size relative to its star. A larger planet blocks more light. If the star's size is known in stellar physics allows us to determine this with confidence. The planet's actual radius follows from simple geometry. The duration of the transit adds another layer. A planet crossing near the star's equator produces a longer event than one that merely grazes the edge. By combining transit duration with orbital period, astronomers can reconstruct the tilt of the orbit and the precise path the planet takes across the stellar disk. Even the shape of the transit matters. Stars are not evenly bright. Their centers glow more intensely than their edges, a phenomenon known as limb darkening. As a planet moves across this uneven surface, the resulting light curve carries subtle distortions. By modeling these distortions, astronomers learn not only about the planet's trajectory, but also about the star itself. Transmission spectroscopy takes this a step further. By observing transits at many wavelengths, astronomers can see how the planet's apparent size changes with color. At wavelengths where atmospheric molecules absorb light, the planet appears slightly larger. Mapping these variations allows scientists to identify the gases present in the atmosphere. Eclipse spectroscopy offers a complementary view. When the planet slips behind its star, its own light disappears. By comparing the system before, during, and after this eclipse, astronomers isolate the planet's contribution. From this they infer the temperature of the day side, the efficiency of heat redistribution, and the composition of the glowing atmosphere. Phase curves complete the picture. As the planet orbits, different portions of its surface rotate into view. Tracking how the system's brightness changes over the orbit allows astronomers to map temperature differences across the planet and trace atmospheric circulation. Together, these techniques form an extraordinary achievement. From nothing more than faint starlight, crossing 1,000 light-years of space, we deduce sizes, masses, temperatures, compositions, and even winds on worlds we will never touch. This is the quiet power of precision. The future of exoplanet science is brighter still. New missions are already on the horizon. Plato, scheduled for launch in 2026, will search for Earth-like planets around Sun-like stars, focusing on worlds and habitable zones, prime targets in the search for life. Ariel, launching in 2029, will survey the atmospheres of around 1,000 exoplanets, building a statistical understanding of how atmospheric properties vary across planetary types. On Earth, the next generation of extremely large telescopes will push direct imaging to new limits. For the first time, they may capture light from Earth-sized planets around nearby stars, worlds that could, in principle, harbor life. All of these advances build on what we are learning now. Hot Jupiters, inflated giants, super-Earths, and mini-Neptunes are not distractions. They are the proving ground. The techniques refined on these extreme worlds will one day be applied to the most delicate targets of all. One day, perhaps, we will detect an unmistakable sign of life and atmospheric imbalance that cannot be explained by geology or chemistry alone. When that moment comes, it will not stand alone. It will rest on decades of work studying planets of every kind, including the most hostile and bizarre. Even the least habitable worlds matter. This planet is one step in that long journey. A record holder today, a data point tomorrow. A puzzle that may one day be solved or may forever resist complete understanding. But it mattered that we found it. It mattered that we tried to understand it. The universe is vast, and most of it remains unknown. Yet every fragment of understanding is a victory against that darkness. The stars are waiting,